Intro to polar coordinates.
Before diving into polar coordinates, let's review the Cartesian coordinate system. Given a Euclidean xy plane using rectangular or Cartesian coordinates x, y to graph functions y equals f of x or other equations like circles is only one way of navigating through the xy plane. So, for example, if we have a coordinate point x, y, recall that this means to move x units to the right if the x value is positive or left if the x value is negative, then move y units up if the y value is positive or down if the y value is negative. So here is an xy plane, and to graph the coordinate point -3, 5, from the origin we move 3 units left and 5 units up. Now let's explore the polar coordinate system. Some curves can be more easily expressed using points of the form r, theta instead of x, y, where r is the directed distance from the pole and theta is the angle with initial side on the polar axis. Let's explore these new terms. So here I have the intersection of two planes, and instead of labeling them the x-axis and the y-axis with this intersection being the origin, we're going to call the intersection the pole when we're talking about the polar coordinate system. And what would normally be the positive x-axis, we're going to call the polar axis. In order to graph polar coordinates of the form r, theta, we actually go to the angle first, and then we address the directed distance r from the pole. For example, here I have the polar coordinate 2, pi over 4. So notice that the coordinate point is an angle measure of pi over 4 away from the polar axis. So here, this is a measurement of pi over 4. And then the value 2 tells me how far away to go from the pole. And because I am a positive 2, I'm going to go towards the angle pi over 4. That's what we mean by directed distance. So in other words, I can count how far away I am from the pole by using these rings. So you'll usually find that the polar coordinate system looks like this, where only the polar axis is labeled, and we have these rings to help guide us a particular distance away from the pole. So now, just for practice, let's go ahead and see what the polar coordinate -2 pi over 4 would look like. So we would go to the angle pi over 4, and instead of going towards pi over 4, because we have a negative directed distance, I would go 2 units away from the pole. So down here, I would label my coordinate point. This is -2, but still positive pi over 4. So first we would have went to the angle pi over 4, and then from the pole we would travel 2 units away from the pole to establish my directed distance of -2. In this example, we're going to go ahead and continue to graph some polar coordinates. Here is our blank polar coordinate system, and I'm going to go ahead and label the polar axis, and I'm going to label just the angles for now in quadrant 1. So we have 0, we have pi over 6, we have pi over 3, and we have pi over 2. So let's go ahead and graph the following polar coordinates. We have A is 2, pi over 6. So what we do is we first go to the angle, so here's the angle pi over 6, and since the directed distance is +2, I go 2 units towards pi over 6, landing me right here as my coordinate point that I'm going to go ahead and label A. Now let's go ahead and try to graph B. Here I have 3, pi over 2. So -pi over 2 is the angle, and a negative angle means that I go in a clockwise direction. So -pi over 2 is down here, and then I go ahead and look at the directed distance. Since the directed distance is positive, I'm going to go from the pole 3 units towards -pi over 2. So that's going to go ahead and bring me down here, and I'll label this point B. Let's go ahead and move on to C. We have -2, comma pi over 3. So here we're going to start at the angle pi over 3. So here it is over here in quadrant 1. However, our directed distance is -2. So instead of going 2 units, going out these like 2 rings towards pi over 3, I'm going to go in the exact opposite direction. So I'm going to go ahead and go 2 units away from pi over 3, landing me right here, and I'm going to label that my point C. So if I'm directly across from pi over 3, I'm still going to have a reference angle of pi over 3. So this angle down here is actually 4 pi over 3. Let's go ahead and try part D. We have -4, comma 3 pi over 4. So 3 pi over 4 isn't labeled for us. This is going to be an angle in quadrant 2, and it's actually going to be halfway between pi over 2 and pi, so halfway between a half and 1 pi, and so we can see that isn't actually drawn here as one of my line angles, but that's okay. I can still go ahead and graph this point. So I want to make sure that I'm halfway between, again, this is 2 pi over 3 and 5 pi over 6, but I actually have a negative directed distance. So instead of going towards 3 pi over 4, so I'll go ahead and draw a line here. This would be positive 3 pi over 4. I'm going to go in the exact opposite direction, which would actually be going towards 7 pi over 4, because my directed distance is negative. So I'm going to go ahead and go 1, 2, 3, 4 units towards 7 pi over 4 away from 3 pi over 4. And then finally, E, I have -4 and then negative pi over 3. So here, we're going to go ahead and go to negative pi over 3, which remember is a clockwise angle. So that's going to be down here. I have negative pi over 3. And whoops, I didn't label this. This is D. So here I have negative pi over 3. But because I have a negative directed distance, instead of going towards negative pi over 3 from the pole, I'm going to go directly away from negative pi over 3. So that's going to lead me towards 2 pi over 3. And I'm going to go 4 units. So 1, 2, 3, 4 rings out, and label that E. In this example, we're going to graph the following regions based on our previous examples and our understanding of these polar coordinates and polar values. So here, this region, this says that the R values are always between 1 and 3. So here we have 1, 2, 3 labeled on our polar axis, so we're always going to be between 1 and 3 in our R values. And then our angles were always going to be between 0 and pi over 2. So 0 is here and pi over 2 is here. So we're graphing an entire region right now. So that region is going to extend from 0 to pi over 2, but be bounded between 1 and 3. And since they're all less than or equal to, these are all going to be solid lines. Oops, that got a little messy. So they're all going to be solid lines here, and we're talking about the region, so I'm going to go ahead and shade in this portion here. So we're graphing inequalities right now that deal with our directed distance and our angle. And then over here, let's just think about what happens if we're restricting the angle theta to be between 2 pi over 3 and 5 pi over 6. So let's recall both of those angles would be over here in quadrant 2. So I have, this is 2 pi over 3 and this is 5 pi over 6. So we're talking about our angle being always between, less than or equal to, so I'm drawing them as solid lines, between 2 pi over 3 and 5 pi over 6. So this portion right here would be part of the region I'm talking about, but because there's no restriction on R at all here, remember that our R's, our directed distances, could also take us directly away from these values in here. So that means that the little pizza slice on the opposite side in quadrant 4 would also be part of this region. In this example, we want to show how to convert from polar coordinates, so 2, 5 pi over 6, and r theta, to a rectangular coordinate, the x, y type of coordinate. So we have a conversion factor here. So if we start with an r and a theta, then to get to an x, y, we're going to have our cosine theta multiplied together as our x value, and our sine theta multiplied together as our y value. And those are coming from our definitions of sine and cosine. Cosine of theta is an x value over the radius, and sine theta is the y value over the radius. So note there can only be one answer. So there's only going to be one answer that comes out here, one rectangular coordinate point, x, y. So let's go ahead and find that. Our x, y is going to be 2 times cosine of 5 pi over 6 and 2 times sine of 5 pi over 6. So now we're going to go ahead and evaluate the trig functions in here. So I have 2 times cosine of 5 pi over 6 would be a negative radical 3 over 2. And then I have 2 times sine of 5 pi over 6. That's going to be a positive 1/2. So notice that the 2's in each of them are going to cancel out. So my coordinate point is going to be negative the square root of 3, 1. And we can just do a brief check just to make sure that we're in the right quadrant. So graphing 2, 5 pi over 6, well, what that would mean is going to the angle 5 pi over 6. So it's right about here. I'd go 2 units towards 5 pi over 6. So just a rough estimate of going 2 units towards this 5 pi over 6 angle. And does that match up with this being an xy coordinate? Well, yeah, because I'd go negative, so I'm over here to the left, and then up 1, so I am in quadrant 2. In this example, we're going to go the other way around. We're going to convert negative 3, 3, a rectangular coordinate, to polar coordinates. But this can actually be done in more than one way. So we're going to represent the coordinate with both r as a positive value and r as a negative value. Let's look at the conversion factors. So to go from rectangular to polar, from xy to r theta, we have to do a little bit of work and a little bit of critical thinking here. So the r value is plus or minus the square root of x squared plus y squared. So we're going to have to choose whether r is positive or negative depending on our angle. So to find our angle, we're going to use tangent inverse of y over x. So to decide the positive or negative, for r, it's based on the quadrant of the coordinate point. And when we find this theta star, that's only going to be the reference angle. So we are going to have to do some thinking about where this point is and how to represent it as a polar coordinate, because polar coordinates can be represented in infinitely many ways. So here, let's go ahead and get started. So we're going to convert negative 3, 3 to polar coordinates. So I'm actually going to start by just plotting negative 3, 3. So I'm just going to do a quick little plot of negative 3, 3. So that's going to lead me over here to quadrant 2. So I'm trying to find a way to represent this particular coordinate point as a polar coordinate in two different ways, with a positive directed distance and a negative directed distance. And you might be thinking, I can actually just figure out what that is by looking at it. And I'm not going to disagree with you, but I want to make sure we can do it for any coordinate point. So we are going to follow this set of formulas over here. So to find r, we're going to go ahead and do r is plus or minus the square root of negative 3 squared plus positive 3 squared. So we're going to have plus or minus the square root of 18, which is plus or minus 3 radical 2. So I'm going to just hold off on that for a second. I'm going to leave those two values. And now I'm going to go ahead and attempt to find what I'm calling theta star, the reference angle. So we're going to do tangent inverse of y over x. So I'm going to go ahead and do theta star is tangent inverse of the y value 3 over the x value -3, or tangent inverse of -1. Now, tangent inverse of -1 is exactly -45 degrees if I use degrees, or -pi/4 if I use radians. So -45 degrees is actually down here in quadrant 4 because tan inverse is restricted to quadrant 1 or 4. So here, down here, is my -45 degrees. So now let's think about how we're going to use this angle and the correct directed distance to navigate someone to this coordinate point. So let's go ahead and start by using -45 degrees. If I am going to use -45 degrees, or -pi/4, then instead of using a positive directed distance, because that would take me down here to quadrant 4, I have to use the negative directed distance because I want to navigate myself up here to quadrant 2. So I have to have -3 radical 2 as my polar coordinate, and that's with r less than 0. Well, if I want to use r greater than 0, if I want to use the positive directed distance, 3 radical 2, then I'm actually going to need to know, well, what is this angle here that's directly across from -45 degrees? Well, in degrees, that's 135 degrees. So basically, this was our reference angle. If I make it positive, this angle here is 45. So I did like 180 minus 45 degrees. That got me to 135 degrees. Or again, in radians, that would be 3 pi/4. So I'll stick with degrees and write 135 degrees.